Let's go ahead and get started. So for today's colloquium, we're going to have another talk in the integrated circuits area. It'll be a fresh look at doing analog and mixed signal circuits, but with a computational flair to it. We'll be looking at a number of applications that are very interesting. And the presenter probably needs no introduction. It is our own Professor Visvesh Sathe. And he is an assistant professor on the cusp of being an associate professor in the ECE department at the University of Washington. His group works on a range of topics surrounding digital, mixed signal, and power circuits and architectures. Prior to joining UW, he served as a member of technical staff in the low power advanced development group at AMD, where his research focused on inventing and developing new technologies in clocking, voltage noise mitigation, and circuit design for energy efficient and high performance computing, which are currently in volume production. That's kind of unusual to work on research chips that actually make it into production when you're at a company like AMD or Intel. I can speak from experience. Dr. Sathe received a bachelor's degree from the Indian Institute of Technology, Bombay in 2001, and the MS and PhD degrees from the University of Michigan, Ann Arbor, in 2004 and 2007, respectively. He currently served as a chapter chair of the Denver Solid State Circuit Society and currently serves as a co-chair of the Seattle chapter of the Solid State Circuit Society. He has previously served as technical program committee member at the Custom Integrated Circuits Conference and as a guest editor for the Journal of Solid State Circuits. He just received the 2019 National Science Foundation Career Award for his work on neural interfaces. So with that, I will turn it over to Professor Sathe.
Thank you, Chris, for that great introduction. Hi, everyone. Thank you for making it over. As Chris mentioned, the purpose of this talk is to really try to have a thought process on how to reframe the way we think about building integrated circuits. That's been done in a traditional manner for many decades now, and we may be on the cusp of looking at this problem in a slightly different way. I think in the interest of what our objective is here, I'd prefer to keep it informal. Feel free to raise your hand if you have a question or if something doesn't make sense, and then we can just go to and fro, and I'll adapt my timing accordingly, all right? So please don't hesitate to ask questions. Before I continue, I want to make sure I acknowledge the current members of my lab who basically did all the work, allowing me to stand in front of you, as well as the ex-students in my lab and those of my collaborators, as well as my collaborators themselves and industry liaisons who we interact with frequently. A lot of the work we plan to do or we work on is done with the mindset of translating it into volume production or actually having an impact in this, in real world applications. So I think, we were all beneficiaries of the advances that computing has made in the last 3 or 4 decades, and they've been stupendous. And I think, it's fair to argue that although circuits hasn't been the only contributor to the advance in computing, it has had a significant role. This role that circuit design has had in computing has actually, if you think about it, not evolved particularly much in the last 2 or 3 decades. We do painstaking circuit design, whether it's digital, analog, mixed signal, detailed, worrying about process variation, environmental effects, and really build a system that's robust, all in service, among other things, to enable computation, right? Now, of course, circuit intensity sort of goes beyond just trying to build and optimize core compute functions. We also employ circuit design in order to be able to implement a large number of supporting subsystems that are very much a part of modern computing today. So, this is just a limited set of examples that are, in many ways just topical, so I've listed them in. There are many, many more. For example, you'll have ADCs and DACs for, allowing a compute system to interface with the real world. You'll have I/O, which is required to connect to memory, connect to other compute nodes. You'll have voltage regulation to be able to target a certain digital system at a given voltage. Power management to orchestrate the power and performance levels of various subsystems in your overall compute solution. You'll have clocking to synchronize and basically time your overall system. And more recently, there's been a need for hardware security to maintain privacy in terms of data that's exchanged between machines. Now, all of these systems and more tend to be very circuit design intensive. And many of them, they straddle digital, mixed signal, and analog design. Now, what's happened in recent years is, as designers heavily mined out the performance and the efficiencies that you could pull out of core compute, whether it's in microarchitecture or circuits in core compute blocks, they started relying more and more on advances in these once support players to deliver the performance and the energy efficiency of the entire system, right? So to drive those advances for the whole system, once you started running out of significant advances within core compute, there's been a heavy reliance on trying to get these subsystems to deliver that performance and efficiency. So for example, at one point, while it was just good enough to have a clock distribution system that was low skew, that had good quality, good edge clocks arriving everywhere in your design at about the same time. Now you wanted, for example, a clock distribution that was tuned to the specific critical paths in your design. You wanted a PLL that could not only maintain a clean clock, but one that would rapidly transition between from and to frequencies when you, for example, went into low energy mode or your laptop went into boost mode. Those quick transitions were suddenly demanded of it. There's a strong push towards integrated voltage regulation to be able to rapidly change your power and performance state in your, in your laptops, on your phones. Machine learning, for example, and data center computing has put a lot of stress on I/O, both in terms of performance and in terms of energy efficiency. Hardware security, for example, is another area which I'll talk about as well. Now, the stress is certainly on all of these, and the traditional approach has been to meet this challenge with more intensity on the circuit design effort. Now, I myself and my group sort of takes the view that not only are pure circuit approaches likely to be suboptimal, they're also likely to be unable to meet these performance requirements that are demanded of these new systems now, right? Instead, we advocate a slightly bidirectional flow. Let's not just focus on circuit design for computing. Let's see all this time that we've advanced in computing, what can computing do for circuit design? And in that sense, can we take some of that compute, put it into each one of our traditionally analog mixed signal or power systems, and use that compute to good effect, and essentially translate what these systems are individually capable of? Right? And that's really sort of the observation that drives a lot of this work. All right, so this sort of set of die shots are basically chip photographs of related work in the space over the last couple of years. Each of these works essentially represents the state of the art in their discipline that's been advanced because of computing. And I don't mean just, robbing Peter to play Paul, essentially sliding along the Pareto optimal curve. What I'm really talking about is computing in each of these examples advances the Pareto optimal frontier to essentially reach state-of-the-art performance in one or more relevant metrics. So for example, and they do so in slightly different ways, which is why they're representative. You can use computing in true random number generation, TRNG, in a slightly more traditional way. Detailed circuit design does a little bit of work, and then you rely on computation to do the rest of it. So you do a balance between computing and analog circuit design, and that basically has yielded the highest efficiency true random number generator demonstrated today. Computing has been used to substantially improve the performance of PLL designs, as demonstrated in this work, which demonstrates a 5x improvement in lock time over the state of the art, and does so robustly. And then the observation there is, instead of implementing PLLs as type 2 PID systems, you instead view the problem of lock as a time domain optimization problem. And the job of PLL lock is one of essentially solving an iterative optimization problem that achieves zero phase error in minimum time. And each reference clock cycle, for those of you familiar with PLLs, is basically an iteration in this iterative optimization problem, right? We've applied computing in the group towards basically doing runtime constrained optimization of an overall system, processor, accelerators, voltage regulator. And there the view is that if we wanted to really optimize the per cycle energy dissipated by the system and do so while providing performance guarantees, so we've got the objective, which is energy efficiency, and the constraint is performance. How do we manage this constrained optimization problem? And it was, until this work, an open problem. And relying on computing and relying on very simple models that are executed at runtime, you can basically perform runtime evaluation and minimum energy tracking. We've also used it in low latency loops. You would think, for example, that if you did a lot of computation, maybe it works for slow control loops, things that don't have to be too rapid. But if you apply these techniques effectively, you can apply computing to pretty much one of the fastest control loop requirements that you can have in IC design, which is low dropout regulators. Extremely fast loop latency requirements. And that's where computing can also do a significant push to the state of the art. Here, basically relying on a time domain model and very simple statistical learning, 1-bit statistical learning. You can basically auto-tune and auto-center an LDO and basically demonstrate the fastest LDO that's been built to date. You can also use it in sort of systems that you think are extremely traditional in terms of their discipline. So neural recording, for example, is a very sort of traditionally analog discipline. If you want more channels, you have to stamp out more instrumentation amplifiers. But if you think of computing in a way that you can roll your analog implementations with memory and compute, it is then possible to basically build a system that achieves a 10x area reduction over the state of the art. So these are just different examples of what computing can do. To do a reasonable job at examining any of these directions, I've basically just picked two of them, the TRNG, true random number generator, as well as the work that does minimum energy tracking. And those are basically the ones that we'll be focusing on. We'll start with sort of the case study with TRNG, then move on to constrained MEP tracking, and then I'll just share some thoughts on where this work is going. Any questions so far before I dive into these? Okay. Right, so true random number generators. What are they and why do I need them? There's a huge push towards security, both on the edge, in your handhelds or in sensors, as well as the data center. The focus that they have is slightly different, but security is certainly an important part of what they play. Cryptography ends up being an underlying platform on which these security considerations are sort of enforced. And where true random number generators come in is that they are efficient hardware primitives that are used by cryptographic applications, right? So that's sort of the importance of TRNGs or true random number generators in the hardware security space, right? And there are key metrics that TRNGs need to have. The thing to note, of course, is before hardware TRNGs came along, you could build almost truly random sequences in software, right? The only downside was they would be dissipative and the bit rate wouldn't be necessarily as high. And it turns out that key metrics that you judge TRNGs on are quality. When you say that they are truly random, how truly random are they, right? Are they pseudo-random, like an LFSR, a linear feedback shift register, gives you pseudo-random code, but you can pretty much predict what's going to happen. That's one extreme. The other extreme is stuff that's truly random, that you have prior history provides no information on what the next bit is going to be, right? So there's a measurement of quality, which is judged by benchmark tests that NIST has provided. There's another set of benchmarks called Big Crush and Little Crush. Efficiency becomes important in mobile and IoT applications. Fine, I'll generate this random number. How much energy am I going to burn in this energy-sensitive application? Throughput and area on the server or the data center side, they're basically requiring gigabits per second of true random number generation, right? How do we get those efficiently at the required quality? And finally, robustness. It's one thing to demonstrate sort of this very sensitive circuit that will extract randomness, on a research workbench, and then when you actually deploy it in a real-world system, it's in a very noisy environment. There is substrate noise, power supply noise, other sources of noise that always bang on the system. And if your system is not robust and it's very sensitive, you're talking about really a circuit that's positioned to be very unbiased, and it can easily be disturbed in a manner that severely degrades its quality, right? So that's where the robustness comes in. So how do we think about true random number generation in hardware, right? So I'm going to provide a very simple abstraction of TRNGs. Not all true random number generators rely on clocked comparators, but I'm going to use this almost without loss of generality. So we'll just examine what it looks like for a comparator, and then we'll go from there, okay? So the basic idea is I have a clocked comparator, which is basically, nowadays it might as well be a digital circuit. You basically, on the rising edge of clock, right? A clocked comparator basically makes the determination whether the positive terminal or the negative terminal is higher. So if the positive terminal has a higher voltage, the output will be high. And if the positive terminal has a lower voltage, the output will be low. What you do is you short the input and rely on the thermal noise, right, that exists in your circuit, and you harness that thermal noise to basically give you random outputs. Convenient, clean so far, okay? Every cycle, I'll fire a clock, I'll get an output that basically samples almost as a delta what the state of noise is and amplifies it and gives me a decision. I've got truly random numbers. Now, what do I care about? I care to make sure that in this ideal comparator, there is never any offset, right? There is no built-in preference because of process variation or because of any other reasons for one terminal over the other. It is a truly unbiased comparator. In other words, the mean of this distribution lines up with the y-axis. You're equally likely to get 0 and 1, and therefore you're equally likely to get 1s and 0s as your random bits. Good so far? All right. Now, this is sort of what the TRNG community has largely been focused on. But there is another narrative, an equally important narrative, and that's one of power spectral density. If you are going to exploit thermal noise, you are really saying that you're going to take all the noise and that's in the entire spectrum from -infinity to infinity in the frequency spectrum, and you're going to harness that noise, and in that, if you're able to truly exploit this infinite frequency range power spectral density, the signal that you extract will be unbiased. In other words, the deviation from the probability of generating a 0 or a 1 is basically 0, it'll be 0.5, right? So no bias. And the autocorrelation of that signal will be a discrete delta, right? In other words, there is no impact of history. Let's look at reality. What happens when you actually try to build these circuits, right? You are going to have process variation. The simple fact that you're constructing these circuits means they are going to have an inbuilt bias for one or the other. You are going to end up with an imbalance. And there is going to be a preference for a 1 or a 0. And the traditional approach has been to design these circuits to death to take this mean of this distribution and make it overlap the y-axis. Do everything we can with very detailed design to remove the bias. Unfortunately, it also turns out that all this while your assumption of being able to harness white noise was fundamentally flawed. You can't do it by virtue of having a real circuit. Any real circuit has finite bandwidth, and therefore any noise that you harness will be filtered. And if you have filtered noise, you cannot have a discrete delta for your autocorrelation. Your bits are going to be correlated with each other. A very simple, intuitive way to think about it is if I have a comparator and if I have finite bandwidth, right? I've evaluated a 1. when the clock goes low, I'm going to go pre-charge both those nodes to 0. But I really need both those nodes to be pre-charged at the same value before the next evaluation. The one that had a history, having been evaluated to 1, is going to approach 0 but not really make it. And when you're talking about amplifying microvolts of noise, you really need those voltages to be bang equal. And that doesn't happen. And that represents itself as an autocorrelation, because in the example that I just provided, you are more likely to reevaluate that same signal that was 1 in the previous cycle to be a 1 again, because it never fully pre-charged, because you have finite bandwidth, right? That's just the beginning of your problems. You also have other sources of noise, such as flicker, that are decidedly non-flat or non-white, okay? So just a quick look at related efforts in the space. You have, there's been plenty of work. I'm just citing 2 of them, done by Sanu Matthew in 2016 and Kai-Yun Yang also in that year. The Matthew work implements basically a highly well-tuned comparator to basically engineer the offset and cancel it out so that you can get low bias, and it actually does a little bit of post-processing to try to clean up the autocorrelation. The complexity involved in this circuit, however, is significant, because the way it's built, you basically need femtoseconds of control of 2 edges that determine the bias in the circuit. So you basically need femtosecond level control of edges that go into your comparator. The work by Kai-Yun Yang is also very interesting. It's very creative. It actually takes care of filtering out flicker. What they basically do is that they have an even stage of ring oscillators, so that they have 2 wavefronts in your ring oscillator, and they wait for them to randomly collapse. And the time taken to collapse is viewed as random, which you then extract randomness out of, right? So that approach is very nice and clean. It filters flicker, but unfortunately, it also filters white noise. And in filtering white noise, you once again get the problem of autocorrelation, which then raises challenges in being able to pass certain NIST benchmarks. So what's our goal? Our goal is to build robust crypto quality random numbers. And the approach we want to take is, let's not rely on carefully designed, highly polished circuits. Let's build circuits that are good enough that can withstand abuse on the field, that can withstand the fact that they are going to be hit by noise, and there is going to be a filtering of the bandwidth that they're trying, bandwidth of the noise that they're trying to extract. So the basic idea is this. Start with a physical random number generator, which is basically just controllably bad, barely good enough. And what you do is, it's going to have a non-zero bias, so you're not going to have equal probability of 50% for your 1s and 0s. You're going to have autocorrelation. So in general, this will never pass a NIST benchmark on its own, right? And I'm not even trying to. I'll just build something that's simple, low power, low area, low complexity, that just gets me at a decent enough starting point. Then I will whiten this noise computationally. What we basically do is we decorrelate this using extremely simple sort of ideas in Markov chains, like very simple. What we then do by whitening it is we basically ideally eradicate the autocorrelation in that bit sequence. It's still biased, but now at least the bits can be viewed as coming out independently of each other. Once that happens, you can use a well-known algorithm referred to as Iterative von Neumann, map it into VLSI, and you basically not reduce bias, but if you have independent bit sequences, you can eliminate bias completely, okay? And that's the approach we're going to take. Circuit effort, moderate, basically digital post-processing at this end. Very robust, very clean, efficient. That's the approach, okay? So we'll basically go through this sort of a block diagram of how it's implemented. We have a strong arm latch. That's a very standard implementation of a comparator, very common. And all we need, and what we do is we do runtime bias compensation, but not nearly at the level required to build a truly random number. We just do this for quality control. We want something good enough. Once we've done that, we basically pass this through what we call a Markov chain router, but you will soon see that it's actually a very, very simple circuit. But that's basically what it's doing. It's taking bits that are not perfectly random, routing them into parallel channels, and it's doing this in a way so that the bits in any one channel are independent with all the other bits in that channel. Now, each of these channels basically contains bits that are independent of each other and potentially biased. That bias is cleaned up to build true random number generators. You basically coalesce all the bits together at the end, and these are more implementation details, and you've got your random number out. So that's basically how the data flows in this system. Okay? Now, a key assumption with being able to correct bias for Neumann correction is that you've got, sorry, it's independent source, not IID. It's an independent source. And what you basically have is, it's a very simple observation. If I have bits that are being generated at a probability other than 0.5, right, there's bias. What the von Neumann approach was simply, well, okay, let me look at bit pairs, basically. Let me look at any two successive bits, and let's observe that the probability of having a 1, 0, with the probability of being 1, let's say, is p, probability of having a 0 is 1 minus p, or p prime. So probability of a 1, 0 is p prime, which is the same as p prime p, which is the same as the probability of having a 0, 1. So if I basically look at bit pairs, and every time I get a 1, 0, I label that as a 1 bit. Every time I get a 0, 1, I label that as a 0 bit. Whenever I get 1, 1s or 0, 0s, I discard them. Okay? Wasteful, but if you have independent sources, it works. Now the downside is that you get a significantly reduced bit rate. Now, remember, you're generating these bits, and every time you're generating a bit, you're dissipating energy. If you're discarding bits, you're hurting your energy efficiency at the system level. At actually a higher level, not the system level yet. So what you really want to do is to minimize the bits that you're discarding. And in the 90s, there was work that was proposed that basically said, well, why should we just look at von Neumann correction at one level? Let's do multi-level or iterative von Neumann. In other words, what you do is, take a bit sequence, such as this one, your 1, 0 pair gets labeled, look at the red output, labeled as a 1 output, 0, 1 gets labeled as a 0 output, 0, 0 and 1, 1s are discarded, a 0, 1 again shows up as a 0, and that's your traditional von Neumann. The iterative von Neumann is built up of these nodes that basically take the discarded bits and say, the basic idea is, let's build a state machine that says, well, why look at just bit pairs? Let's look at pairs of bit pairs and pairs of bit pairs and extract higher order statistics in order to get the bits that we want that are also random. So you basically propagate these bits down a tree, right? And the way they basically propagate down, you're now, the T pins or the von Neumann, sort of one level von Neumann corrector, lower down the hierarchy is basically generating random bits from higher order bit patterns, right? And the more of these you build, the more random bits you're able to get out. But the cost is that every time you go lower, your throughput basically drops by a factor of half, right? So the first highest level extractor gives you a good rate. You've got less rate, and then there's a trade-off. You have to figure out the optimal tree shape and the optimal tree size where you're investing energy to get the most number of random bits out, right? And that's a straightforward optimization. It's a design time optimization. Nothing you have to do at runtime. But the key is that this is nothing but a finite state machine. Give me input bits, I will update my state, and I will spit out 3 outputs. That's all I'm doing. Just a simple digital state machine. Okay? Now the catch was this. All this was great, but I needed an independent source. And my physical random number generator did not have that. So the basic observation that enables this was as follows. Most types of correlation can be modeled reasonably effectively with a Markov chain model. And for those who are not familiar with Markov chains, don't be turned off. We're applying it in its simplest form. So it can be very easily described. All we are doing is we're basically tracking the probability of an outcome based on what the previous outcome was. So I'm just going to label this state as a 0 if its previous outcome was a 0. It's a coin flip or a random bit. So all I'm saying with this figure is, oh, if the previous output was a 0, the probability of staying at a 0 is 0.4, probability of switching to a 1 is 0.6. And same if you were 0.6, it kind of favors flipping over. This kind of a system, you can tell, is unbiased. It will generate unbiased bits. Unfortunately, it will also generate correlated bits. And this is the correlation that we want to fix. So the basic observation was, well, if I can use a Markov chain model to essentially model most of the sources of correlation, I can use that same model at runtime to then unravel that correlation and basically generate uncorrelated bit streams. So how am I going to do that? Very simple. I'm going to track what Markov state I'm in. I'm going to make an a priori assumption that, oh, this process has a certain complexity. We don't use a two-state Markov chain. This is just for a simplified description. We happen to use a four-state. So we're tracking the last 4 outcomes in the actual chip. But here we're just going to show that we're tracking the last outcome. What am I doing? By default, let's say I start in state 0. I get an input, happens to be a 0. It gets routed to a lane whose index is my Markov state. So this goes straight to lane 0. Next input, I'm in Markov state 0, route to 1. What was the previous output? 1. I update my state, I'm in Markov state 1. Whatever bit I get now gets routed over to lane 1. I stay in lane 1 because my last output was a 1. I now generate a 0, and it goes on and so forth. But what's the catch? The catch is this. In any one lane, the bits that are in that lane came from the same Markov state. In other words, they have the same statistics, right? They don't have statistics that are different from each other. And in that sense, there is no reason for them to have a probability of being a 1 or a 0 that's any different from the others, right? Now you've basically whitened this source, provided you have captured enough Markovs, captured enough history in this system. And you basically take this whitening process, you take the iterative von Neumann implementation, and you just directly map them into VLSI. Turns out to be straightforward. The physical random number generator goes into that so-called Markov chain router. That is nothing but a shift register. What am I doing when I'm tracking which Markov state I'm in? I'm just tracking what the history of the bits was. That's the shift register. That's all it is. So I'm taking my bits, sending them into a shift register, and I'm using those to essentially load and store this register file. I'm observing that my state machine, if I have 16 lanes for bias correction, I'm only using 1 lane at a time. The remaining 15 are not being used. So the way to save area and power is to store the state of each finite state machine in the register file, load it based on the state machine or the lane that's selected by the Markov router, do the correction, and store the updated state, and you get your random number out. That's all I'm doing. And this is the 65 nanometer test chip that was implemented. The key is you want to build just a good enough physical random number generator. This is the effective area of that system. So the physical random number generator is very small, very simple, and then you're just relying on a bunch of placed and routed logic to do the rest. So I'll sort of move ahead in the interest of sort of capturing the key components. Why are we doing all this? Other than for efficiency, we also want to prove robustness. So, and that's really what we're after with this plot, okay? So what we're showing in this plot on the y-axis is the voltage at which the system is operating on the x-axis. And on the y-axis, we have the entropy, okay? Yes, if you truly are interested in randomness, you would be tracking entropy rate. But it's common to sort of plot entropy in the literature, so we're just being consistent for now. We're just basically looking at resulting bias, and that's where the entropy comes from. What we're doing is we're going to track 2 things, the physical random number generator, the TRNG, and the true random number generator outputs. We have access to both of them, right? And what we're going to do is at 1.05 volts, we're going to sort of basically run our feedback corrector, correct the bias in the circuit, build relatively unbiased outputs in the physical random number generator so that they have some decent balance. So basically, relatively high entropy at a good 1.05. Not enough to pass NIST, but they're decent. Then what we do is we turn off the bias correction. That is always typically running. We turn it off and scale the voltage. And sure enough, as the voltage drops, and you're not making adjustments in real time based on that different voltage and different bias correction condition, your physical random number entropy drops. In other words, the bits are more biased. The quality of your physical random number generator is completely tanked, right? What we want is for our TRNG to maintain its quality even though it's getting lousy physical random number generator bits. And that's exactly what this demonstrates. We're kind of zooming in onto that part of the axis, and you're able to maintain a very high quality randomness even though your source of randomness has degraded. There is no free lunch. We are providing these qualities at the cost of energy efficiency. So if you have a really lousy physical random number generator, you're going to dissipate more energy, but you're still going to be able to provide a quality assurance. That's the problem we're solving. And the test chip demonstrates the measured autocorrelation ends up falling in line with what we expect. You basically have an autocorrelation delta, a discrete delta for lag 0, and then it's below the noise autocorrelation floor for the rest of the lags. And we ran these through NIST benchmarks, including, importantly, the updated NIST benchmarks that has added particular focus on correlation between bits. And the test chip bit streams basically not only pass both benchmarks, but they do so at different voltages across a range of temperatures, and that's the robustness that a serious true random number generator needs to have. Okay? So that's sort of the TRNG aspect of how computation can easily attach itself to circuit design and allow for a more balanced system design. Now we'll sort of take another track. We'll look at the problem of low energy computing, right? It's been around for a while, 2 decades that I'm aware of at the very least. There's been a lot of talk of doing sub-threshold circuits. There's been a lot of work in that space as well. Very low voltage circuits for very high efficiency. And there are a lot of takers for this. It's valuable in sensors, in edge computing. You can, there's certainly use for it in implantable devices. But here are where the challenges are. You can provide energy efficient computing, but for that to actually have an impact in the real world, you need to solve 2 niggling problems that have been relative, well, 3 problems in this case, that have really been stubborn till now. The first is, I'm not really interested in just the total energy dissipation of a little piece of circuit. I'm interested in the total energy dissipation. How much does my battery have to give out at the end of the day? Accounting for the voltage regulators, accounting for all the other systems that are in the design. I'm interested in total energy dissipation, first. Second, minimum energy is of absolutely no use, right? And then there's a very common pitch that's done for IoT. We'll do really low energy sort of computing. It's of absolutely no use if you cannot provide a minimum level of performance and you cannot guarantee that performance. You have to provide performance guarantees for any practical real world system. Otherwise, it's quite frankly not of much use. Third, when you do low voltage design, you actually have to provide a lot of margins. Low voltage circuits are very sensitive to environmental factors like temperature, supply noise, and you have to aggressively margin for them with an extra voltage so that the circuits are safe and they don't slow down and fail timing, things like that. And these margins are prohibitive. By the time you account for all those margins, the whole value proposition for low voltage design begins to erode, right? So what is minimum energy, right? How do you get a minimum energy? If I want minimum energy, why don't I just scale the voltage close to 0 and I'll keep getting lower and lower energy? It doesn't work that way. And the reason it doesn't work that way is that your energy per cycle, or EPC, is made up of 2 components, switching losses and leakage. All circuits leak. And that is the catch, right? So you'll have switching losses in blue. As you scale the voltage, you will see your energy per cycle drop quadratically. That's great, right? That makes the argument for a lower voltage for lower switching energy. However, you also have leakage. And the deal with leakage is, even though as you scale the voltage, your current drops and you're leaking less and your power drops, what happens is your circuit slows down more than it reduces its leakage, in a manner of speaking. And therefore, when you look at the leakage energy, the amount of energy that has leaked by the time you've completed a computation, Now over a longer period of time, because you're running at a lower voltage, that energy is actually going up. Naturally, when you add both of these, you've got a minimum energy point. There's an optimal energy point, which we call VMEP, voltage minimum energy point. That's the voltage we always want to run at. So that's easy. Dial it in, run the system at that voltage, and you're done. Not entirely, right? Before we go into that, the thing to note is if you have a certain voltage at the minimum energy point, you have a corresponding operating frequency for that minimum energy point. Remember, we're not just interested in energy, we want to provide assurances on performance. So we have to keep an eye on what the corresponding frequency is, in this case FMEP, the frequency corresponding to the minimum energy point. Here's the problem. In digital circuits, because of temperature variation in large part, the leakage curve actually moves around a lot. If you're in a high temperature environment, this curve moves out. If the temperature is low, it moves in. So there's a huge temperature dependence, and this curve is thrashing about. Your digital circuit is in some DC current. Depending on what computations are being performed, whether it's sort of chugging away without any cache misses, you've got lots of energy. If it's stalling for memory very frequently, for example, the curve's on the lower side, you end up with an uncertainty band. And your interest is in actually tracking this minimum energy point. That's what we want to go after. So if I dial my minimum energy point, as a necessary consequence, when I start playing with the voltage my circuits are running at, the frequency at which that they'll run at, naturally, is updated. So I'm going to have different frequencies that I'm going to be running the system at if I want to hunt for minimum energy. Here's a catch. Let's say my minimum energy point evolves over time. Temperature variations, loading variations, whatever. And that's all I do. I just track the minimum energy point. My frequency will naturally evolve, which is fine, except if I have a target requirement, which is typical of any real-world application. Now, if I purely just hunt for minimum energy, I've basically got a system that's useless, right? So that's the first thing. We need to make sure we provide performance guarantees. There has been prior literature in minimum energy tracking, and it's really the only one that I'm aware of, by Yogesh Ramdas about 10 years ago. And the problem that they were trying to solve at that point was purely minimum energy tracking. And the idea was, well, let's take a whole bunch of energy, put it on a capacitor, and sample that voltage. Having that capacitor now power my entire system with no other sources, just my capacitor. I will run the processor for n cycles. I'll discharge this capacitor, and after those n cycles, I will measure what the voltage of that, what the voltage across that capacitor was. The difference in voltages, if I just take the difference of half CV squares, gives me a sense of how much energy was given up by this capacitor that was used for storage, right? That's the basic idea. And this is constantly run and operated to make sure that you can run for n cycles with minimum discharge of your capacitor. In other words, you're dissipating your minimum CV square difference in your capacitor. So you're dissipating as little energy as possible in order to run your processor for n cycles. With the benefit of hindsight and sort of a different set of problems that we're looking at, this work was great, but it doesn't happen to address a number of considerations. For example, it relies on sort of significant analog design to get things right. It requires a significant capacitor to be put there so you can actually run a processor for many cycles. So that's a big capacitor. It has essentially got a sampling and readout accuracy problem. Well, limitation, not problem. In other words, if you put a huge capacitor, there will hardly be any change in voltage, and you need to be very accurate in measuring the voltage change. If you have a small capacitor, you'll have a huge change in voltage, which you can easily detect. But now, you're really not taking a snapshot of energy at a given voltage point. It's over an entire duration. And you can't just take the average, because that's not how leakage works, right? And finally, and crucially, this work minimizes only the energy dissipation in the actual load circuit. It doesn't actually minimize the total energy dissipation. And that's really what we're after. We're after figuring out how to get the total system to dissipate as little energy as possible. And for that, you have to include not only the minimum energy point of one circuit, but the minimum energy point of all the circuits that are in your system, and include any regulator losses. You will very rarely have a circuit that runs on a battery that doesn't have a regulator. That regulator has losses, and by the time you account for everything, you end up with a minimum energy point that's quite different. And we are interested in tracking total minimum energy. And not only do that, can we do that computationally without relying on detailed circuits that we have to craft carefully, right? And that's sort of the objective of this work. So what do we envision? What should a system like this look like? A system that's actually useful. First, let's say the green curve on a frequency time plot, over time you have this green curve which could be the demanded frequency of your processing system as requested by the operating system or by a power performance management unit, okay? The blue curve, which I'm just going to claim that I happen to know what it looks like, I won't, but we'll see about that soon, is the FMEP, which is if I actually know what the minimum energy voltage is, I know the corresponding FMEP, and that fluctuates depending on temperature and loading. That's my FMEP, and that's going to evolve over time. I'm going to pretend for now that I know what that curve looks like, because that's completely dependent on what the circuit's doing, what the temperature is. I have to figure out what that curve is, but let's pretend I know what it is. What the system should be doing is when the target frequency requirement exceeds FMEP, it basically runs in what we call perf lock, performance lock. I'm going to run in order to guarantee what the performance of this system is going to be, okay? Then, if my operating system requests a lower frequency of operation, I'm going to autonomously transition into MEP tracking, minimum energy tracking. In other words, I'm actually running faster than I'm required to, but don't worry, that's more energy efficient, okay? And that continuously tracks any variations in the minimum energy point, and it autonomously detects if that frequency is dropped below my target, and if it's dropped below my target, I need to switch back to performance lock, and at all times I have to guarantee that the clock frequency I'm running at always exceeds the target, okay? And that basically forms my performance guarantee. So how do I know what my MEP is? I pretended like I knew what the blue curve was. I don't. Unfortunately, the answer to this is a little bit boring, but it is also the most effective. I'm just going to sense it. I'm just going to sample it. Every now and then, when I'm running in performance lock, I'm just going to take a quick deep dive, track my minimum energy point, sample it, know what it is, put it into my memory, go back into performance lock. This is a very brief duration, which I can account for. It's any performance loss that may occur. But now I know at a relatively frequent enough beat what my minimum energy point is like. And if my required frequency drops below it, I'm going to autonomously switch to minimum energy operation, right? So I just rely on sampling. So what do we do? When we're running in performance lock, we basically have a system, and this is basically what we built in our chip, is a complete integrated system with a microprocessor, FFT, accelerators, and we use a voltage regulator to power the system. We used a technique called Unicap, which is stuff that my group and others have worked on in the past, but that's completely a separate talk. The benefit of Unicap is that it allows you to promise what a performance requirement is going to be by virtually eliminating margins. So that addresses the first problem, which is can you do low energy design without prohibitive margins, okay? So doing Unicap essentially is a technique that allows you to operate your system by virtually eliminating required margins, and the basic trick to that is to basically build a PLL, but having the PLL absorb the voltage regulator. So we're literally merging two traditionally disparate fields, voltage regulation and PLL design, into one combined system, and that sort of fusion gets you this unprecedented capability for margin removal, right? But that's a completely different piece of work, so I won't go into that. You basically run into in performance lock using Unicap, and then when the system, I'll sort of skip through these, and when the system needs to operate at minimum energy, then you've got this MEP controller, minimum energy point controller, that says, no, don't run in performance lock. It hijacks the regulator control, and it dials in different target voltages and evaluates their energies so that it arrives at it figures out what the voltage is that corresponds to minimum energy. Okay? So how does it figure out what the minimum energy is? Our plan is very simple. Let's change our voltages while the system is operating. All this while, by the way, we are not messing with processor operation. The processor is continuing uninterrupted, unaware of all these changes going on. They're happening on the side to the processor, okay? So it's happening uninterrupted. You're making all these changes, and the plan is to figure out what voltage corresponds to minimum energy. Well, how do you know what that energy is? Do you need some kind of energy meter? That's been something that's been bothering the community for a while. The angle we take is a very different one. And that's simply that it turns out that the energy dissipation model for these systems is actually quite trivial. Let's just implement that model through computation at runtime. In other words, if I look, if you don't understand switch capacitors, you're not familiar, that's not important, right? The key thing to observe is that the way a switch capacitor regulator delivers energy to a processor is by essentially charging and discharging this flying capacitor. And all we are going to do, quite simply, forget all the details, is just going to look at the amount of charge that I have to deliver from the supply. If I'm tracking how much charge is required by my supply, I know how much draw is there from the battery. That's it. That's all I need to do. The rest is essentially details, right? I can track the amount of charge leaving my supply. There's a straightforward equation for that, right? So the supply voltage times the amount of charge I delivered happens to be equal to some function of my Vin and my output voltage and a flying capacitor value that I need to dial in. When I'm operating this system, I can basically use that energy total value, scale it by the switching frequency of the switch cap, basically known quantities, and now I can basically get the energy per cycle. I've basically taken a very simple model that is understood, that doesn't vary from chip to chip, and literally I'm going to perform inline computations by sensing the relevant parameters in the equation and determining what my total energy is, and I'm able to do that very cheaply and digitally. So, let's say you have this expression. How are you going to get this? Like, total energy per cycle depends on all these parameters. Great. I need to compute them. How do I do that? We rely on the circuit to give us the answers, right? And we do so without interfering in its operation. So what we do is, all right, let's look at all the parameters. Vin and FSC, these are basically operational constants. Those are the ones that you dial in when you run the system. Easy. Next, VDD and C-fly. VDD is actually when you're making adjustments to run the supply voltage you want, that's the VDD that you're applying. So that's a known quantity. C-fly is what the closed loop operation of the system is giving you. The system is telling you what amount of regulator parameter is required, in this case flying capacitance, to regulate the system at the current draw and at the voltage that you want. So C-fly is an answer that the circuit gives you. And you just basically pull that out and you know C-fly. F-clock is directly measured by the PLL by repurposing the PLL that you already had. And this is a readily attainable number. And now you've basically gotten all the relevant parameters that you care about by simply either knowing what they were to begin with or simply interrogating your closed loop while it was operating, right? And to do so, we basically built out a microprocessor with an FFT accelerator, switch capacitor, voltage regulator, and the controller itself takes very little area, and its energy overhead is small. More importantly, you can timeshare this controller. It's not constantly operating, right? You can timeshare it between many other modules, and that further cuts down its area overhead, although the energy overhead is going to be what it is. And we also had a switch capacitor module, and I'm just going to share some sort of measurement results with you that demonstrate the system in operation. So first, we're going to show how the system transitions from performance lock to MEP track to performance lock. This oscilloscope trace on the chip is showing you what the supply voltage of the system was. The thing to bear in mind is, in the unicap loop, the way you are getting a target frequency is by setting a target voltage. That's sort of the key thing to remember. Why is incidental at this point? If I have a fixed VDD, that my closed loop system is basically setting VDD so that I have a fixed target frequency. I am locked, I am phase locked at this point to my reference clock at a frequency I want to run. If the operating system says, no, go into MEP track, the system transitions, and what it basically then does is constantly hunts for the minimum energy point. Throughout this sequence, a microprocessor is running uninterrupted. No change in what the processor itself is computing. And you can see that in these durations, the MEP point is actually adjusting. In these durations, for example, here, these correspond to regions of higher switching activity in the processor. The MEP tracker basically updates itself to essentially lower switching activity. It raises its voltage in order to be able to achieve minimum energy. When the switching activity goes back up, it goes back down. The VDD goes back down. And that's basically what it's doing until you require performance lock again, and it autonomously transitions back into phase locked operation. What it has to do when it first gets into MEP is it actually has to perform a search and then eventually track the MEP. And that search and tracking operation is basically done using sort of a successive refinement, sort of pseudo gradient descent approach, right? But it's a very straightforward approach, so not really worth discussing in detail for a presentation such as this. Now that's great. You can transition from performance lock to minimum energy. What if you have this system and for reasons required by the application, you are occasionally turning on your FFT, right? When you turn on your FFT, your switching activity goes up. The switching losses go up, the MEP point shifts. Your autonomous system better track that. And you have to verify that that's what's going on. And this is what this experiment shows. The plot itself is a VDD capture, so the supply voltage that the autonomous system is basically applying. Over time, as I have a cortex and the FFT turned on, then I turn off the FFT, I turn on the FFT, and so on and so forth. And as I'm going through these periods of activity of the FFT, this control loop is basically making sure that it is always finding the minimum energy point. Sure enough, when it's only the cortex and there is reduced switching activity, the system naturally determines it's better to run at a higher voltage with higher switching losses, but I'll finish my computation quicker and I will leak less. And it does so and autonomously switches its voltage to a higher value, back down, back up, and so on and so forth. So you can basically keep dialing in different amounts of switching activity, and this system will naturally adapt to whatever voltage gives you minimum energy, throughout ensuring that at no point your system operates at a performance that is lower than your application demands. That's the constraint that it must meet. And I'll sort of share this sort of view here. My grad student took a lot of time to gather data on. And the Y plot you've got is energy per cycle. X-axis is VDD. Each of these curves corresponds to a different computational load seen by the system. And in this case, we just took something simple. We ran you either operate with just the cortex, which is just the microprocessor core. You run it with the FFT that's throttled. And then you keep reducing the throttle until you get to the green curve where you're running the cortex and the FFT is banging away at max frequency. Maximum switching activity, minimum switching activity, okay? And it's running whatever benchmarks ARM provides us while running this system. So what we did was each dot on each one of these curves is a bench measurement, right? Obviously, the student wrote code for this, but it's a bench measurement. And what we're doing is we're explicitly measuring what the total energy dissipation of the system is at each of these points for every candidate voltage. And we get an energy per cycle versus VDD curve, right? The square corresponds to the minimum of each of these curves, the minima, right? Then what we then did was, okay, now we know what the system dissipates and what the energy curve looks like from detailed explicit measurements. Now let's unhook all our measurement equipment, run the autonomous MEP tracker, and see what it does. And the cross corresponds to the point that the system lands itself at. And the gap between the square and the cross is within 5 millivolts, which is the resolution of the voltage update of the system. So it does a pretty good job in terms of actually finding the minimum energy when it needs to. And this difference corresponds to basically a 14% EPC difference. This is not improving, and this is a sobering point that must be made. We're not suddenly taking a system and making it 10 times more efficient, right? We're just talking about 15–20% improvements. And sure, Unicap on top of this will give you another 45–50% improvements, but again, that's a separate talk. These are improvements that you basically take to the bank. These actually will translate to real world savings, as opposed to sort of stuff that will whittle down as you actually deploy it, right? So in conclusion, sort of from whatever experiments we've tried, and we've tried 4 or 5 systems now that take a computational angle to designing integrated circuits and systems, whether they're analog, mixed signal, power, or digital, we're finding that it's a promising enabler. And so far, we've really largely depended on sort of advanced control or simple optimization strategies. So we try to use computation to implement more advanced control than exists in IC designs today, or we deploy simple optimization strategies. And we've also found, our learning has been that actually modeling the system accurately and leveraging computation to track that model has been a really good enabler to achieving advances in these systems. So our measurements support the case for compute-augmented circuits, and we've sort of done that across the space from random number generators, PLLs, voltage regulators, down to neural recording. And sorry, those are my backup. So we're good. On time. Thanks.
Okay, let's open it up for questioning. Questions, not questioning. We're not at the police station.
Yeah.
Yes, Greg.
When you're going into the search phase, do you see a fairly significant increase in noise? Let's say that was being distributed to the entire system.
So you're talking about when I'm in this search phase, what's up with this, for example, right? So it turns out that you have to cater to that. The fact of the matter is, when you're going into search phase, you have to, that's a good question. You have to make sure that if you're searching for an energy, right, a voltage point, you better pass timing on that point. So if you're operating at a certain performance value, you're trying a different voltage, you better not run at a frequency that's higher than the voltage you're trying for. And you have to enforce that by doing the construction that we did with that Unicap approach with a ring oscillator that's locked to through a phase lock. So when you're actually trying different candidate voltages, that counts as noise, right? But the clock frequency of the system is adjusted in lockstep organically as you're dialing in voltage. So your voltage is your only independent variable, and your frequency becomes your dependent variable. It automatically adjusts so that you never fail timing. So yes, there is noise, but yes, you can tolerate it because you don't lose function.
More questions? I have a question. Actually, so on the random number generators, what is it called? Neumann correction?
Yeah, von Neumann correction.
What does it say?
Von Neumann?
Von Neumann correction. That helps you with offset and any offset that's in the comparator itself. But how does it help you with the bandwidth question? Because the comparator still has the limited bandwidth, and I thought that was leading to.
Yes. So that's absolutely right. Your von Neumann correction is only for debiasing. It does nothing for autocorrelation. You have to perform autocorrelation before you do bias removal, because von Neumann correction relies on independent bit streams. So where the correction of the autocorrelation function is happening is not happening with von Neumann correction. In fact, von Neumann correction, autocorrelation is a constraint for von Neumann correction. So if you want to do von Neumann, you cannot have autocorrelation. You better go fix that problem before you run this algorithm. And the way that's done is basically with this so-called Markov chain router, which is really nothing but a shift register. right? And what you're doing is you're saying, look at the history. Based on the history of these bit streams, I'm going to route a random bit into one of these candidate channels. Now, the property is going to be that in any one channel, the bits that are in that channel came from the same Markov state. In other words, they have the same history, and therefore, they have the same probability distribution. There is stuff having to do with flicker noise, but that's kind of a separate conversation. It's this routing that's providing the whitening that you need. This is fixing the autocorrelation to a large extent, and then the bias removal is just removing the bias.
So this is going to be a dumb question, but in the comparator, could you address some of these issues if you simply coupled, say, had a pre-gain stage and you coupled it? So basically what you're doing is you're taking the noise from the first stage and you're amplifying it across a larger range. So trying to take advantage of the full scale of your, say, the comparator itself.
So I want to make sure I understand this. I think what you're saying is, can you have a preamp that's wide bandwidth, maybe a little bit more power, and you almost pipeline the operation so that you hand it off to a second
Actually,
stage?
so what I asked, so that doesn't help you with the bandwidth question. I was getting back to this offset question, I guess.
Right.
So in order to overcome the offset, could you just amplify it, then couple it into the next stage? Just AC couple it into the next stage.
Oh, you could?
So then the basically what I'm trying to do is get the noise distribution to be wider across a wider range.
Yes.
And I don't know if that simple circuit trick has been explored or.
So I'm not aware of
Or maybe it doesn't work.
anyone having explored it, and that will definitely allow your second stage to be far more liberal in terms of the offset that it can have. But I wonder whether the offset of the first stage remains something that you need to fix.
Oh, I see. Yep. Couldn't you just couple it? Actually, we'll take it offline.
Sure.
Okay, more questions? Anything? Okay, well, let's thank our speaker one more time.